Let's try and understand coagulation. Now, in case of colloidal particles, what did we observe? That colloidal particles have preferential adsorption of ions on the surface. Now, for example, here what I have shown is this is the colloidal particle which has adsorbed cations on its surface. So this becomes cationic colloid. Alright. Now furthermore, colloids are of two types. One is lyophilic, another is lyophobic. As the name suggests, philic is loving, phobic is hating. So lyo, liquid loving. Alright. These colloids have great affinity for dispersion medium. If these salts are stripped of dispersion medium by evaporation, these stripped salts when remixed with medium would form sol once again. Alright, so lyophilic colloids are the one where they again get back, even if we remove the dispersion medium by evaporation, then what happens is we get these solid colloids. We get the solid colloid particle. But to this solid colloid particle, if we add dispersion medium again, they get back into lyophilic colloids. So that's the reason why we call it as reversible salt. Examples are starch, rubber, gum, gelatin. We know, right? Starch, if we put it back in water, again it gets into colloidal form. Starch, right? So quite natural. We have seen it. Now, let's talk about lyophobic. Once precipitated or coagulated, having least tendency. So if it is precipitated or coagulated, they have least, these lyophobic colloids particles have least tendency to get back to colloidal state. Alright, so that's the difference between this. So these are called as irreversible salt. Irreversible salts are FeOH thrice, AlOH thrice, arsenious sulfide. Alright, now let's get into actual theme, that is coagulation. Let's understand charge-wise situation of colloids. Now colloidal particle, these are all what I have shown as colloidal particles. These are the colloidal particles which I have just magnified over here. Now we are assuming that it has preferentially adsorbed positive ion or rather cation on its surfaces. Alright. Now since it has adsorbed cation on its surface, so the matrix or the dispersion medium would be negatively charged. Now that's what I've tried to show over here. Now I've just outlined it with red color, indicating that the colloidal surface, colloidal particle surface are all positively charged and this negatively charged is of matrix. So what happens is, so that's the reason why even they have repulsion, but there's attraction from the matrix, owing to which they stand like this. Alright, so they don't fall down or they don't repel and go away like that. So the matrix keeps them attracted, owing to which it's one of the best, this is one of the best state for colloidal situation. Alright, so that's the reason why. Now by some means, if we are able to destroy these charges, then we would find this situation. Alright, all charges destroyed. As a result of that, there won't be any attraction from the matrix or the dispersion medium, and there won't be any charge on the colloidal particle, owing to which there's no issue of charge, so it would all drop down and coagulate. Alright, okay, let's understand the means by which we can carry on the process of coagulation. Electrophoresis is the one which we already saw, where colloidal particles charge gets discharged on moving towards oppositely charged electrodes. Alright, that's what we saw. So it goes there and gets discharged and then it's coagulated. Alright, by mixing equal proportion of two oppositely charged salts. Yeah, very obvious. So suppose we have taken FeOH thrice ferric hydroxide, which is a positive salt, mix it with arsenious sulfide, which is negative salt. They coagulate each other mutually. Alright, so this is yet another. By boiling, what happens by boiling? We know by boiling, lots of disturbance is created in the system. Alright, so adsorbed layer is disturbed as a result of increased collision with dispersion medium, reducing charge on particles, promoting coagulation. Alright, so boiling is also yet another process by which coagulation can be preferred. Alright, now let's try and understand Hardy-Schulze rule. Now it's by adding electrolytes. Flocculating power is coagulating power. Flocculating power of Al3 plus is greater than Ba2 plus, greater than Na plus for negative salts. So what do you understand? Charge. Greater the charge, greater the flocculating power. Similarly in case of anions also. FeCN6, 4 minus, 3 minus, 2 minus, 1 minus. So this is the greatest for positive salts. Alright, so what is Hardy-Schulze rule? It's greater the valence of flocculating ion added, greater is the power of coagulation, or greater is the power for coagulation. Alright,